For starters, the first, call it programming assignment, is due on Monday. This will kind of be the test to make sure everybody has their Linux distribution installed. So I'm actually going to demo it really quickly for you, so you'll effectively just mimic what I'm about to do for that homework assignment. Just because we won't quite get to that the Python aspect of it for by the end of class today. So, and it's only going to take 30 seconds here. So you will go into your Raspbian virtual machine. Let me shut this. So your virtual machine is going to look something like this when you first launch it. Go up to the little Raspberry guy up here. Go to programming. All the way down here at the bottom is this Thorny Python IDE. It's as good as any. That's what we'll be doing our examples in, but it's just a text editor for doing Python stuff. So go ahead and click on that. You'll put your program here at the top. So you'll say File, New. So, to print out Hello World, you say print Hello World like that. Go ahead and save your file like homework1.py. And then to run it, hit play. There's your Hello World. Do a screenshot of this and submit it as your homework. Make sense? Good.
Do you have to do PI at the end?
For a Python file, that's the correct MIME type for a Python file. It actually, I think, will work without it, but it would be good to get into the practice of it because this one will work without it, but it won't work without a .py in all cases. Yeah, so just like a Word document ends in a .doc or a .docx, a Python file ends in a .py. All right, so that's the homework for Monday. So you'll duplicate that, and that means you have your whole environment set up and that kind of stuff. Yeah, I think I say submit a screenshot of it. All right, something else you might start doing if you go to Blackboard. On the left-hand side, it's a click on Course Book, and that'll take you into something that looks like this. If you scroll down, you probably you could read through Chapter 0, most of it we've already talked about, and then start reading through Chapter 1. You actually won't need anything. You just saw what we did there for the first homework assignment, but you're going to fairly quickly here going to need stuff from Chapter 1. So I would make it a point to start reading through Chapter 1 of the book. Maybe if you try to get through that for Monday, that might be good, but if you at least make a pretty solid dent, that'll get you ahead of the curve. Okay. One of the things it talks about is using the interactive shell. So even though we're running our Python program here where we typed a bunch of stuff in and hit play, you can also, say I equals 5, print I, stuff like that. This is what they're talking about with the interactive shell. So you can feed it Python stuff. I equals I times 7. Print I, stuff like that. So you can work with the interactive shell with Python commands to test different things out and see how they work. That's typically not what you'll do when you're actually writing your code. You'll write it up here in a file that has a whole bunch of lines of code that you intend to do something. But if you want to test out to see if a certain sequence does what you think it's supposed to do, using the interactive Python shell is beneficial. All right, so that's mostly what Chapter 0 has you, or Chapter 1 rather, has you mess with. It introduces the Python shell and then has you type some different things in and introduces some different stuff. And we'll be going through Chapter 1 most of next week. I just need to get through some of the other material first. Sound good? All right. So, end of last class, we talked about, we decided we were going to start talking about the CPU. If you remember the slide right before this, we talked about machine language versus low level versus high level. So, ultimately, our computers here speak zeros and ones. It speaks machine language. Now, in the middle here, we have this thing called a low-level language, which has a one-to-one relationship with the CPU. We'll talk about that here in a minute. And then we have this high-level programming language, like Python, like Java, like C++, C#, so on and so forth. These are our power tools. These are the languages where every line of code we write translates into a whole bunch of things on the CPU. And to really understand what this stuff means, we have to understand the nature of the CPU. So I'll ask, what is the CPU? Everybody will say, oh, it's the central processing unit. Then I'll say, well, what does it actually do? So when we're talking to our computer, when we're telling our computer what to do, ultimately, we are talking to the CPU. The CPU is the guy that's going to carry out our instructions. So I like to think of the CPU as a collection of magic tricks, where each trick solves a very tiny problem that might not be that interesting in and of itself. But when you chain a bunch of magic tricks together, something real might happen. All right, so like the folks at Intel, when they made the Core i5, Core i7 processors, or the older processors, whatever it is, what they did is they said, okay, here's this processor. So think of it like a little basket, and here's all sorts of things it knows how to do. I'm calling them magic tricks. All right, they're little tiny computer programs created in hardware. All right, so hardware is actually how the programs are made. Now, each of those programs, each of those magic tricks does something very, very, very tiny. It might move a value from here to here. Okay, it might add some value to another value, storing the result here. So things like that is what it's actually doing. Now, nobody's impressed if you take the number 7 and move it from here over to here. That doesn't seem that useful in and of itself. But you do enough of these magic tricks in a row, all of a sudden, a real solution to a problem has happened. Okay? So a low-level language here would require us to tell the CPU every tiny little instruction. Do this, then this, then this, then this, then this. And that can be pretty tedious. Now I'm going to make a comment here. So programs target an architecture and an operating system. Now, we've talked about computer operating systems. When you hear computer architecture, does that mean anything to anybody? What is a computer architecture?
32-bit.
Okay, so that would be part of the starting point for our architecture. I mentioned a few minutes ago, like a Core i7, Core i5 processor. Go ahead.
I think of the foundations and how the computer is built. Like, when you think of architecture, you think of how things are built.
Yeah, the structure of something.
Yes.
Yep. So when we think about computer architecture, generally what we're really talking about is the collection of magic tricks we are working with. And that's done in terms of, so this is in terms of the CPU we are working with. So that is the design of that CPU. Intel created this physical structure. That is that CPU, and inside that physical structure, they gave it a bunch of features, a bunch of these magic tricks. So in terms of the CPU, we intend our program, well, let's see, let's make sure we have it grammatically, our CPU on which we intend to run our program. All right, so that's one thing we're targeting when we write a program, when we compile a program. This will make sense in a second. The other thing is our operating system. We've talked about operating systems in here, Windows 95, or really it's the 9X kernel, or the NT kernel, or the Unix kernel, Linux kernel. The operating system provides a collection of, I can call it magic tricks if we want to just keep the analogy going, okay? But a lot of times this would be called system calls, or the operating system's API, that allow us to accomplish complex but common things more conveniently. All right, so when we write a computer program and we ultimately use whatever tool we use to get it into the position where it'll actually run on our computer, which can happen through compilers or interpreters, which we have not talked about compilers versus interpreters yet, right? That's fine. So however that occurs, we target two different things. What kind of CPU is this going to run on, and what operating system is driving that CPU? All right. And in order to explore this a little bit, I'm going to go through the Linux Hello World assembly program. All right, so this is a low-level language in i386 Intel-based assembly language, specifically targeting, so it's targeting that architecture, let's call it, it's targeting the Intel architecture, and it's also targeting the Linux operating system. And that's important that we're targeting both of those things here, because I promise this low-level language will look much, much, much scarier once the system calls, the magic tricks of the operating system, get exploded out into their low-level language that's actually occurring here. So we're going to talk about how this kind of works. Remember, I said, way human beings solve problems is we remember things, we ask questions, and repetition, right? And I said 100% of programming languages have facilities for these things. So down here in our data section, you don't have to memorize this or anything, we are remembering a couple of things. We're remembering a variable called MSG, and that guy is equal to hello world. We are remembering a variable called len, and that's equal to, that's the length of message. So the number of characters that are in message, that's what that guy comes down to. So this is hello world, this is the number of characters in hello world. We're remembering two pieces of information. All right, so now remember, I talked about low-level languages have a one-to-one relationship with the CPU. So every line of code we write here, so this is where the program starts, start label. So every line of code we write here translates into exactly one magic trick on the CPU. All right, now these things here, EDX, ECX, EBX, EAX, these are these things called hardware registers. So your CPU has these little memory locations on them that are effectively variables built out of hardware. Really, 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 really fast. So what are we doing here? We are moving the value of length into this little memory bucket. Then we're moving the value of message into this little memory bucket. Then we're just arbitrarily moving the number 1 into this little memory bucket. Then we're moving arbitrarily the number 4 into this memory bucket. Then we're going to interrupt the CPU and ask the operating system to take over, calling the kernel. Now, the way operating systems work is once they take over and they're going to perform one of their system calls, one of their magic tricks, the first place Linux goes and looks at is what is inside of EAX. It checks that bucket, and it finds in there the number 4. And the number 4 just happens to correspond to the magic trick on the Linux operating system called syswrite, which knows how to write something to the screen. I promise that's a really complex program that will be lots and lots and lots of lines of assembly code that we don't have to write because we're leveraging our operating system as a power tool. Does that make sense? Now, would you agree that one of the things that's pretty common for operating systems to do is to write something to the screen? That's a pretty common task, so it kind of makes sense that that's one of the magic tricks an operating system knows how to accomplish. Okay, so the first thing the kernel, this is operating systems are called kernels. First thing the kernel does is it looks in EAX and it says, what do you want me to do? It says, I want you to perform magic trick number 4, which happens to be syswrite. It says, okay, well, magic trick number 4, syswrite, requires 3 parameters to work. I need to know where do you want me to write it. I need to know what you want me to write. Really what you're telling it is the beginning of what you want to write. And then how long is it? Because it starts at the beginning and then writes out characters some number of times until it runs out to the end. That's why we need to know the length. So syswrite requires 3 parameters to work. Where am I writing it? What am I writing? How long is it? So after it finds out that you want magic trick number 4, it's going to look in this memory bucket for the where am I writing it. Just so happens in the Linux operating system, standard output, which is our screen, is considered output 1. Okay? So it's a number we are writing out to the screen. That's what the 1 means. Then it's going to check ECX, another memory location. And this says, where is the beginning of my message in system memory? So that'll take you right to the very beginning where the H is. Then EDX will store the number of characters in Hello World. All right, so it says, this is what I'm going to do. Here's my 3 pieces of information I need to work. Now it can go and perform that magic trick and ultimately write out the H, then the E, then the L, then the L, then the O, blah, 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 blah. Make sense? So now Hello World's on the screen. Then we return back to the assembly program here. The next instruction to the CPU is to move a different value into EAX. Remember, Linux checked EAX first before. It looks inside of EAX and says, what do you want me to do? What magic trick should I perform? So we load into EAX before we call upon the operating system to do something. We don't always have to leverage the operating system. The operating system just happens to have some power tools that we might want to take advantage of in our programs to make really complex things easier for us so that we don't have to figure out the magic of writing through our graphics card and have it ultimately talking to the monitor. Somebody else already wrote that for us. Okay? So I'm going to go ahead and replace the value that used to be in EAX, which is a 4. I'm going to replace it with a 1. Now, I didn't touch these other values. They're still sitting in those 3 memory locations. But after I load into EAX, the number 1, I'm going to ask the operating system to take over again. What does the Linux kernel do? The first place it goes is it looks in EAX and it says, what is it that you want me to accomplish? It sees that you want me to accomplish magic trick number 1, which happens to be sysexit, end the program. And sysexit doesn't require any parameters, so it's not going to look in any of those other buckets for inputs. It's just going to make the program die. Program is over. That make sense? This is Hello World written in a low-level language that leverages, so it's written in the low-level language for the Intel architecture. So i386 architecture is usually what it's called. So it's a low-level language written in the Intel architecture specifically for the Linux operating system. If we looked at the same Hello World program in Intel architecture targeting Windows, so the NT kernel, it would look similar-ish, but it would be different, right? Windows looks in a different bucket for the command. The system calls are different. Instead of calling it syswrite, it's called something else. And it might not be magic trick 4, it might be magic trick 13, right? So things like that will shift as you go from between operating systems, but you're really using both of those variables. What's my architecture? What's my set of magic tricks the CPU understands? And then what's my set of magic tricks my operating system knows about? And you're solving your problems in terms of those 2 things. Make sense? All right, so we just looked at this. We all followed this as we walked through it, right? And I'm telling you that this is using significant power tools from the operating system to accomplish this task. This was the easy version of Hello World in assembly code. Now, this was Hello World in Python. Which do you like better? This one? This one's geekier, right? This one's cooler. It's like, I'm glad I saw that. And in a pinch, if I was in industry and I had to do some project that maybe required me to get down at the low level thing, this looks English-like enough that we're like, I could probably do this for a short period of time, right? We can handle this. We couldn't handle a wall of zeros and ones. I promise each of these commands, this guy translates into some 8-bit command, some series of zeros and ones that relates to the move command. Then this guy is referenced by some series of zeros and ones. So it's kind of like remembering a phone number. You know, what's the 8-bit, a series of values? Actually, I think it's 5 bits for registers, but whatever. What's the series of values for the EDX register? Human beings would prefer to type in EDX than tap out a bunch of zeros and ones. Okay, so we definitely don't want the machine language thing. We could tolerate this for a bit, but we really prefer this. Make sense? This is a high-level language. This one line of code here, even though we're dealing with an interpreted language, which we'll talk about in a second, relatively speaking, is actually all of this. Okay? That makes some sense? All right, so when we write our programs, we care about what the architecture is, and we care about what the operating system is. But what's nice for us is we don't have to deal with that because we have tools that do it for us. There are two kinds of programming languages. We have compiled languages. Oop, spelled it. Ay. And we have interpreted languages. I'm going to throw something else out here. There are two kinds of programming languages. Kind of the same slide, but we're looking at it from a slightly different angle. We have loosely typed and we have strongly typed. Now, I'm going to label our languages quickly and then come back and give some definition to these. So I'm going to scroll back up here to our history of our languages, this picture right here. And I'm going to label these guys as loosely typed, and I'm also going to label them as interpreted. And I'll throw a little punchline here and say relatively slow. These guys over here are strongly typed, compiled, relatively fast. So all of our native programming languages tend to be strongly typed languages. They tend to be compiled languages. They tend to be relatively fast. Web languages, loosely typed, interpreted, relatively slow. All right, so let's talk about what these different things mean briefly. So compiled languages convert the code into low level prior to runtime. Interpreted languages convert the code. It actually doesn't convert it, but we're just to keep it simple, we're going to use it, we're going to say it this way. Convert the code into low level during runtime. Okay, this is, if you're listening to somebody give a speech in a different language on TV and you hear that interpreter who's turning it into English, there's a little delay, right? So that would be relatively slow if it had to go through some interpreter while it's running. That make sense? So that's why interpreted languages are considered relatively slow. Compiled languages are considered relatively fast. Now we have a software tool called a compiler. Now, a compiler is a software tool that takes a high-level language, that is, languages that humans like, as input, and outputs a low-level language for a particular architecture and OS, kind of what we just talked about. It targets an architecture and an operating system. So we had this cool power tool called a compiler, which is really, really complex to write. So we're going to say compilers are very complex to create. So if we were going to give some a connection to this, we see many, many new interpreted languages come out all of the time, but rarely is there a new compiled language. There tends to be kind of a language of the week when we're looking at our web languages. Everybody and their brother comes out with an interpreter for something else because they're very simple to write relative to a compiler. Because a compiler is actually solving an extra difficult problem. Not only does it have to take your high-level code, your C++, let's say, and turn it into accurate low-level code for the Intel processor for the Linux operating system, it furthermore wants it to be optimized low-level code for the Intel architecture for the Linux operating system, so it runs quickly. Maybe we might even say one of the jobs of a compiler is to make a mediocre programmer look like a good programmer at the low level. All right, because it's turning your high-level code into equivalent logic, but maybe more efficient low-level code. But that's what this tool called a compiler does. Now, ultimately, we have another tool that we often don't need to use directly, but there's a tool called a linker. So a linker takes low-level code and creates an executable capable of running on a target architecture and OS. So it takes all of your compiled programs that are in low level and turns it into machine code that will actually run on that operating system. Okay. Usually when you run a compiler, the last step of the compiler software package will be to link your code, producing a executable. If you actually want to see the low-level code that comes out of a compiler, you have to tell it, don't do the linking process. Show me your low-level code output, and then you can look at it. Okay? So this is what a compiler does. This is what that tool does. And remember, all of these languages over here are compiled languages. They're also all strongly typed languages. So what does it mean for a language to be strongly typed? Well, loosely typed, this all has to do with deal with memory when we create variables. Loosely typed does not require us to define the kind of value that will live inside of a variable. Strongly typed does require us to define the kind of value that will live inside of a variable. What does this translate into? In a loosely typed language, we need a type inference engine. Fancy way of saying a program that figures out what is in a variable before it lets you do things with it. Okay, so for example, If you're going to do some math with a variable named a, it makes sure that that variable is mathable. Okay, so if I'm going to show you the example over here, I can go ahead and I can say something like a is equal to 5, b is equal to a plus 3, print out b. And the output of this guy should be an 8. Because when I go to add a to 3, it's going to try to resolve this variable. And the type inference engine is going to look inside of a and say, is that guy a number I can do math with? Or as I sometimes say, is it a mathable number? All right. In this case, it looks legit. There's my 8. But what if I put inside of a hello? And then I try to do this. Now, it screams at me and says, not a mathable number. Really, it's talking about concatenation. It's treating this guy as something different. But the point is it's using a type inference engine to accomplish this. If I were writing this, I'm just going to use this space here to write the equivalent code in like C++, Java. So I would say int a is equal to 5. Int b is equal to a plus 3. And then I'll just fake it. The print function is not a real function in Java. It's system. I'll just write it. We'll do system.out.println b. All right. So notice here that in a strongly typed language, I had to say this variable I'm building is capable of holding an integer. This variable I'm building is capable of holding an integer. Make sense? I'm doing that prior to runtime. So when I compile this program, it's already flagged A and B here as being buckets for holding integers. Where in Python, I can flip-flop. I can say A equals 5, B equals A plus 3, print B. Then I can say A is equal to hello, print A. And it's cool with that. So a few minutes ago, A held a number. Now, A holds a string. I just arbitrarily used that piece of Tupperware to hold a different kind of value. Loosely typed languages let you accomplish that. But to give you that flexibility, you now have an artificial slowdown because you have this extra program floating around called a type inference engine that at all times has to keep an eye on your variables and make sure that what you're trying to do with them is something that can be done, right? You don't do math with something that isn't mathable, for example. All right, so because of that type inference engine, a Python program would run relatively slower than a C++ program because a C++ program doesn't need to figure out what kind of type is currently in a variable. It knows what's in there because the box, that variable container, is already labeled. There's a piece of tape on it that says int. If it's advertised as having an int, you're not allowed to put things that aren't ints in there. Make sense? So it's relatively faster, strongly typed languages are, whereas loosely typed languages, so this is relatively slow, this is relatively fast. So we look at this, if we were to look at this in broad strokes, our native languages are relatively fast languages. Our web languages are relatively slow languages. What kinds of things do we use our native languages for writing? We use it for writing operating systems and video games and other applications that might need to be as fast as possible, let's say. A couple of these guys, namely Java and C#, are kind of hybrid languages. C# does become native at runtime, but Java actually is an interpreted language at runtime because everything runs through something called the Java virtual machine. All right. So you probably would not write a video game or an operating system in Java, even though you could. So this guy would kind of live somewhere in the middle. Faster than these dudes, but technically slower than like C and C++ or Objective-C. All right. But I say relatively slow and relatively fast. Why is that? Good. Either.
They're still both going to be really fast.
Why? Why are they still going to be really fast? This guy's fast, right? Our computers are really, really, really fast. They're faster today than they've ever been. In fact, they're so fast today that we can't make them really any faster. So what do we keep doing? We just keep adding more cores. Our computers can now do more things at one time, right? Instead of just doing one thing at once, it can do 8 things at once or 16 things at once or, whatever, consumer level stuff. Maybe it can do, you might have a quad core processor, so it can physically do 4 things at once, sort of, kind of 8. But punchline is we just make it do more things at one time, which then makes the operating systems more complex, because now you have to teach your operating system how do you decide which things can happen at the same time versus which things are required a previous step to have occurred before I can do it. I can't print out the value of A until A has a value, right? So I can't do those 2 things at the same time. I'm reliant on A getting a value first, and then I can print out A. So my operating system needs to be able to figure out which things are reliant on other things and not try to do those at the same time, and which things are completely independent and we can do those at the same time. The cleanest way of doing that is saying anything that's part of one computer application can happen, presumably has to happen in the order in which it was defined, where you can have another program running on a different processor, something like that. All right. But punchline for us here is that our computers are really, really, really fast. And for 99% of all applications you might ever write, Python is going to feel just as fast as C++. To the human eye, we're not going to perceive a speed difference if you try to print out 100,000 numbers versus C++ printing out 100,000 numbers. It's going to feel the same to us. That make sense? So if I come back over here and I say for I in range 0 to 100,000, print I, and then I run this, that program's going to run just as fast as if I do the same thing in Java. Now what's interesting here, you see it's still running, right? I'm going to create a variable here called sum. I'll start it off at 0. And then I'll say sum is equal to sum plus I. And then I'll just print out the final value of sum at the end. So this program's still running, right? Look at how fast it ran that time. Same program. Except I did math in here. And I printed one time instead of printing every time. What does that tell you? Printing is expensive. Outputting to the screen is expensive. It takes time to do that. Every single time we wanted to write something out to the screen, I had to interrupt the processor and let the operating system take over. Over and over and over 100,000 times. We saw how long that was taking to run. In this case, I'm just doing math. Processors are really fast at doing math. And then I interrupted the processor at the very, very end and said, print something. Make sense? So I promise if I wrote this in a different language with all those print statements inside of the for loop, it would have still taken a long time to run. Go ahead.
Why is that number at the bottom not like just 100,000?
Because we are summing it up each time. So this is 1, 1 plus 2, 2 plus 3, so on and so forth. Yeah. Just the logic we're actually doing here. If we decided to count instead, and each time we said count is equal to count plus 1, and then we printed out count. Now we get our 100,000. It's the number of times I went through there. All right. Don't worry about any of this stuff right now. I'm just giving you examples of some stuff. We'll go back through and talk about what all this stuff is. All right. So we recognize these are relatively slow, these are relatively fast, but our computers make everything fast. All right, so we only really need to care about that when we're considering what's the right tool for the job for a particular application we're trying to write. But What I'm telling you is that the problem over here, having a brand new language over here, is way, way, way more difficult, because you have to invent a compiler that knows how to take this high-level language, turn it into efficient low-level language that then runs on the operating system. Where for these guys over here, what are they doing? They're writing the interpreter, the PHP interpreter, the Ruby interpreter, the Python interpreter. They're writing it in one of these languages that already exists. So maybe the Python interpreter is written in C++. So they wrote it in that, which already has a efficient compiler. It's been out for a couple of minutes. And they write that interpreter so that when you type in the command in Python, print something, it turns that in, it uses the equivalent instructions for C++ to accomplish that. Does that make sense? So we're not actually getting low-level code out of the Python interpreter. Instead, the Python interpreter is a computer program that was written in some other compiled language that says, oh, you want to do the Python print? No problem. I'll print stuff out as if I was printing it in C or C++, because this program was already written. All right? So it's very easy to create an interpreter where you can come up with your own magical syntax for your made-up language, because ultimately it's running on something written in one of these guys. Okay? That's why interpreted languages are relatively slow, and that's why compiled languages are relatively fast. Now, what's interesting here is our interpreted languages also tend to be loosely typed, which isn't necessarily a requisite for interpreted languages. There's nothing that says you can't make an interpreted language that happens to have strongly typed variables, but they tend to not be. My opinion on that is the folks that typically use these languages, maybe in the early days, now it's maybe more tradition, but maybe in the early days, these were less accomplished programmers, less experienced programmers who they wanted to keep the syntax to somewhat of a bare minimum. Don't have to type extra things. All right? And that comes now with the consequence of being able to do something like I had up here before, where I had A is equal to 5 and then A is equal to hello. So no semicolons. That doesn't really make sense. Typically, even if you're in a loosely typed language, when you create a variable, you're going to put a certain kind of value in there, and that's the kind of value that will remain in that variable from that point forward. You probably wouldn't necessarily like switch value types later on, because it wouldn't really be compatible with your problem-solving logic. But technically, a loosely typed language allows you to do that. Just because a language lets you do something doesn't mean you should. All right, so punchline for us is Python is going to be a interpreted language. It's going to be a loosely typed language. It's going to be a high-level language, power tool for human beings, so that we can write one line of code and have it translate into a bunch of magic tricks on the CPU. Make sense? All right, so let's talk about types. Call these guys primitive types. So we're actually going to go back. My argument is that all of our modern languages come from C as a base language. So we're going to talk about the primitive types in C. These are the kinds of values we can create variables to store by default. All right, so we have something called a byte, short, int, long, char, float, double, Boolean. All right, so these guys hold whole integer values. Whole integer values, whole integer values, whole integer values. Why do I need 4 different types all capable of holding whole numbers, like the number 7? I can hold the number 7 in a byte. I can hold the number 7 in a short. I can hold the number 7 in an int. I can hold the number 7 in a long. Why do I need so many different ways of holding whole numbers? Keep in mind, these are the primitive types from C from 1968. What do you think? Go ahead.
Depends how big the whole value is.
Okay. So we'll add a little stuff here. So this is going to be a byte is 8 bits. That's an 8-bit whole integer value. A short is a 16-bit whole integer value. An int is a 32-bit whole integer value. And a long is a 64-bit whole integer value. Why do we care? Oh, yeah, come on in if you want.
Okay. Hello.
All right, so why do we need 4 different ways of holding these kind of values? Thinking about 1968. Give you a quick example here. Let's talk about memory. How many of you have a computer that has at least 4 gigabytes of memory in it? How many have 8? 16? 32? 64? All right, so why do you have 32 gigs of RAM? Just because I want it. For games? So you think when you play your games, it's taking up all 32 gigs? Well, yeah, you probably can run your game off of 8. 16 is probably overkill already. But we'll operate off of this. So let's say some of you have 8 gigs of RAM. Several of you had your hands up for 8, right? What if you wanted to double the memory in your computer? You want to go out and buy 8 gigs of RAM for your computer. How much would 8 gigs of RAM today cost? 6, that's probably even high, right? But we'll use so we're going to say in 2020, 8 gigabytes of memory, you're going to say is $60, right? All right. So we're going to go back to 1996. I bought 8 megabytes of memory. Okay? 8 megabytes of memory. Now, a megabyte is much smaller than a gigabyte. Okay, we're going to see how much smaller at the beginning of next class. But 8 megabytes, how much do you think I paid for 8 megabytes of memory? Go ahead. 150? Keep going.
200.
Keep going.
500.
$1,000. $1,000. All right. So 8 gigabytes of memory times 1,024 is 8192 megabytes. Divide that by, well, so that's how many I have from that. So I'm going to say 60 divided by that, $60. So we'll say 6,060. I'm just going to write down this number first. 8192. So this is actually 8192 megabytes for $60, or 8 megabytes for $1,000. So 8192 divided by Why am I getting strange numbers from this? So this is 6. So less than a penny. So this is roughly half a cent per megabyte. Whereas down here, this was $125 per megabyte. Less than a penny per megabyte today, $125 per megabyte back then. And I'm telling you, this was already after memory started coming down in price. It had already gotten cheaper. So you can imagine that back in 1968, we had to be pretty careful about how big the values we were storing were, because memory was crazy expensive. All right, so next class, you have your homework due for Monday, but next class we're going to talk about size conversions. And then we're going to talk about number conversions. All right, questions, comments, concerns, bribes? I'll see everybody on Monday.